Hello everybody, welcome to the first lecture of MA180, MA190, MA186 Calculus for semester 2. My name is Rachel Quinlan and it's a big pleasure to be working with all of you in this semester. So here on the screen you can see our first weekly problem. Every week we'll have a weekly problem, which is a little puzzle for a bit of distraction for people who enjoy such things. It's nothing really to do with our curriculum, but we can have a look at it while we're getting set up in the mornings. So there's the first one. If anyone's interested in these weekly puzzles and if you have a solution that you'd like to share with the class or just with me, just please let me know by email and I'll be very happy to share it with everybody if you would like that. So yeah, there's the first one. They're tricky puzzles, I think, but they're quite interesting ones. Okay, the weekly puzzles, however, are not our main business, so I'm going to stop sharing that one and instead share the first section of our lecture notes. So for an introduction to our lecture content and what to expect during the semester, please have a look at the welcome video that's on the main course page. So our theme for the first few weeks is integral calculus. Give me there a second. And so in this first lecture, we're going to just have a look at a fairly simple problem, but one that illustrates one of the key concepts of integral calculus. Okay, so section 1.1 is called areas under curves, and we're just going to look at a few examples. And so the first question that we'll ask ourselves is one that is quite straightforward and can be answered indeed without any reference to calculus at all. And our question is, we've got a car that's traveling for 1 minute at a constant speed of 10 meters per second. And our question is, how far does the car travel within this 1 minute period? So, okay, the answer to that is, well, we're traveling 10 meters in each second, and we're traveling for 60 seconds. So, of course, we travel 60 times 10 meters, which is 600 meters. So it's not a difficult problem, but it's one that actually might be taken as a starting point for some more complicated problems that arise quite frequently in calculus and indeed in lots of applications of mathematics as well. So we're going to make this problem a little bit more complicated for ourselves, but see also how this kind of most basic version of it already has some interesting interpretations that we might be able to carry further. Okay, so that question, even though it's a very simple question, and even though we can answer it without sort of having to do any extra analysis, we can give it a graphical interpretation. So suppose that we draw a graph of the car's speed against time. So the speed here is on the y-axis. It's constant for this particular problem throughout the time period. So this 10 is 10 meters per second. We're measuring time in seconds, and we're starting at time 0 and finishing at time 60. And of course, we know that if we travel 10 meters in each second and we travel for 60 seconds, then we're traveling a total of 60 times 10 meters, which is 600 meters. But the thing to observe here is that we can actually interpret that in terms of the graph as the area of this red rectangle. So it's the number of meters per second, which is 10. That's the height of the rectangle multiplied by the number of seconds. Gives us the 600 meters, which is the distance traveled. Okay, so that's an observation. And of course, we can answer this question without having to think about areas of rectangles, but that is an interpretation of the answer that we have given. Okay, fine. Of course, we can ask a few variants of the question. Here's a variant of it. So in this version, the car travels at 10 meters per second for the first 20 seconds, at 12 meters per second for the next 20 seconds, and at 14 meters per second for the last 20 seconds. Okay, the question is the same. What's the distance traveled? And of course, this question is no harder than the previous one. We have 3 periods of constant speed, and for each of those 3 periods, it's easy to figure out the distance traveled. So, 20 seconds at 10 meters per second, that's 200 meters. 20 seconds at 12 meters per second, that's 240 meters, and so on. And we can add up the 3 blocks of distance. The picture this time, well, the graph of our speed against time, we can draw in the same way. It's the upper boundary of this region. So it consists of 3 separate horizontal line segments, each of them corresponding to a 20-second subinterval, and the heights being 10, 12, and 14. And again, we can observe that the total distance traveled is the area under that graph between time 0, which is the left-hand boundary of the picture, and time 60. Okay, so that's fine. We can study such things. The question, of course, in this particular version is physically not very realistic, because the speed at which a car is traveling can't instantaneously jump from 10 meters per second to 12 meters per second. It would have to continuously pass through the intermediate speeds in between those. Okay, so this question is a physically unrealistic one, but nevertheless a sort of approximately credible one for which we can give an answer, because we're talking about cars traveling at constant speeds, essentially. Okay, here's another version of the same problem, and again, it's not any more interesting. Same setup. We're traveling again for a minute. This time again, it's a physically unrealistic setup where we are imagining that the speed at which our car is traveling can have discontinuous jumps in it, that we travel at 10 meters per second for the first 5 seconds, then it increases to 11 meters per second for the next 5, and so on. It increases by 1 meter per second every 5 seconds, so that after 11 of those increases for the last 5 seconds of the interval, we're traveling at 21 meters per second. And so again, the problem is to calculate the total distance. And again, we can conceptualize it as the sum of the areas of a bunch of rectangles, each of them which is 5 seconds wide, and which has a height corresponding to the speed, the constant speed during that particular 5-second interval. And we can figure that out easily if we want to, what the answer would be for that case. So here, in the first 5 seconds, we're going to travel 50 meters. In the last 5 seconds, we're going to travel 5 times 21 meters, and we can figure out the total if we want to. I won't expect you necessarily to do that. Okay, here's the question we really want to talk about, a harder but more realistic one. So supposing that our car is again traveling for 1 minute, but this time its speed is increasing, not in discontinuous jumps, but at a constant rate from 10 meters per second at the start of the minute to 20 meters per second at the end of the minute. Okay, so the speed in this case is changing instantaneously, which is more in keeping with the principles that calculus can study, which are things that are continuously changing. It's also, of course, physically realistic in that this is something that could actually happen, that a car could have a steady acceleration from 10 meters per second at the start of a 1 minute period to 20 meters per second at the end of it. And the question is the same: what's the distance traveled in that situation? Okay, this is harder. And in principle, we should have enough information to give an answer because we have complete information about what's happening at every instant during the minute. But we can't apply this idea of taking the constant speed and multiplying it by the length of time that we're traveling, because the speed is not constant, it's varying all the time. So how do we make this calculation? What do we do? Okay, so this is where the sort of idea of thinking about the total speed, the total distance traveled as the area that's enclosed under the graph that tells you how the speed varies with time over the relevant time period might be relevant if it can be adapted to this situation. So on the next slide, we have a sort of hypothesis, I suppose, where we have a picture of this problem, again, as a graph, which shows the car's speed against time. So the upper boundary here is the part that's relevant of the graph, this sloping line segment. That pink line is actually the graph that tells us the speed at any particular time during the 1 minute interval. It's increasing steadily from 10 meters per second at time 0 to 20 meters per second at time 60 seconds. Okay, and again, if it's true that the total distance traveled over that 1 minute, again, in this case, can be represented as the area enclosed under the speed graph between time 0 and time 60, then we can calculate that area. It's just the area of this rectangular piece, which is colored in red, that has width 60 and height 10 meters per second, plus the area of the triangle that's sitting above it, which has height 10, the total increase from 10 to 20, and width also 60. So if that's plausible, if it's true, if it gives us truly the distance, the answer should be 900 meters. The area of the red rectangle is 600, and the area of the blue square of the blue triangle is half of that. It's half of 60 times 10. Okay, fine. That's a sort of hypothetical answer based on the assumption that in this case, as in the case of constant speed, the area under the speed graph is the thing that captures the distance traveled. So really the main theme for this first lecture is, why should we believe that? Just because that's true when the speed is constant, why should it be true also when the speed is varying? Okay, so the explanation for that, I'm going to try to give it in the context of this very particular sort of simplified application, but it can also, it is the explanation that works in all cases if one is faced with the problem of calculating the area under a graph where you know the function whose graph is in question. And that's sort of the theory of what's called Riemann integration. And so we're going to do a version of it for this particular problem, but it applies in much more abstract and much more general contexts. Okay, does this make sense that we should consider this to be the area under the graph? Well, let's think about it. Okay, so the question is, just because the distance is given by the area under the graph, when the speed is constant, why should we believe that that should also be the case where the speed is varying continuously? So in the last problem, the speed increases steadily from 10 to 20 meters per second over the 60 seconds. We want to calculate the distance. So something that we can do is we can take our 60-second interval and we can divide it into 30-second intervals. So we have the first 2 seconds from 0 to 2, we have the next 2 seconds from 2 to 4, the next 2 seconds from 4 to 6, and so on. So at the start of the first interval, we know that the speed is 10 meters per second. Okay, so if we just pretend, which is not accurate, that the speed remains at 10 meters per second for the first 2 seconds, then we would travel 20 meters in the first 2 seconds. Okay, that underestimates the true distance because we know that the speed isn't constant to 10 meters per second throughout that 2-second interval. It's increasing from 10 meters per second. So this estimate fails to take that into account. It just sort of starts at 10 and assumes that the speed stays there for the first 2 seconds. Okay, at the start of the second 2-second interval, we've completed the first 1/30th of our total acceleration. The total acceleration is 10 meters per second from 10 to 20 meters per second. So, in the first 2 seconds, 1/30th of that acceleration is completed. So the speeds at which the car is traveling at the start of the second 2-second interval is 10 plus 1/3 of 10. Sorry, pardon me. It's 10 plus 1/30th of 10. We've completed 1/30th of our acceleration. So it's 10 plus 1/3 meters per second. If we were to assume, which again underestimates the truth, that the speed were to stay constant at that value, so the speed here is 10 and 1/3 meters per second. If it were to stay there for 2 seconds, then the distance traveled in the second 2-second interval would be 20 and 2/3 meters. Then the speed at the start of the third 2-second interval is 10 and 2/3, and so on. So this is explained in the next slide a bit better. Okay, if we break the whole thing up into these 2-second intervals and make the simplifying assumption that throughout each 2-second interval, the speed remains constant at the level that is at the start of that 2-second interval, which we can calculate because we know how the speed is varying, then we'd have these 30 sort of vertical columns whose area would add up to an estimate of the total distance traveled. Okay, so we could do that. And if we did it for the whole 30 2-second intervals, you can satisfy yourselves that I'm not deceiving you here, that you would get 890 meters as an estimate throughout the whole 1-minute period of travel. Okay, we know that that's an underestimate of the true story because we know that at each stage, in each 2-second interval, we're actually underestimating the true value. Okay, so that's an approach to trying to get an estimate. Okay, and we can, of course, you don't have to take 2-second intervals. There was no particular reason to do that. Okay, the picture that we would get in that case would have 30 2-second intervals. So here it is, and we can see that in the first 10 seconds, we have 5 of these 30 2-second intervals. At each stage, we're imagining that the speed stays constant at the 2-second interval at the value that it's at the start of that. So that increases by 1/3 for each of the 30 2-second intervals, making a total increase of 10 as we travel from the left to the right ends of the picture. Okay, so we get 2 times 10 plus 2 times 10 and 1/3 plus 2 times 10 and 2/3, and so on right the way along. So we would get the total area of those rectangles that are written in red. What we can say for sure is that estimate, which turns out to be 890 meters, might be reasonably accurate, but it's less than the true value because it fails to take into account the acceleration that's occurring throughout each 2-second interval. Okay, and also the other observation, I suppose, from this picture is that the speed graph is the sloping black line there. The red area of these 30 vertical columns accounts for most of the area under the speed graph, but what it omits is 30 small triangles, which are kind of written there, visible there in white, just under the black sloped line, each of which has base length 2 and height 1/3. Okay, so you can, of course, calculate the total area of those things if you want to. Okay, and of course, if you want to take, instead of taking 30 2-second intervals, if you wanted, you could take 60 1-second intervals. Same thing, in that case, the increase in speed from one interval to the next would be 1/6, not 1/3. You'd have 60 intervals instead of 30. And if you did that, you can again check if you want to, that your estimate of the true distance traveled, of the total distance traveled, will be 895 meters. It's still an underestimate because it still ignores the acceleration that happens throughout each 1 second interval. Okay, and so on. We can get better estimates basically by taking finer partitions of the interval, by taking smaller subintervals and more of them. Okay, so the thesis, and this is really kind of the central concept in this that drives the subject of Riemann integration, which is this problem of calculating areas under curves, is that the true area under the curve should be the limit of this process as you take finer and finer subintervals and more of them. Okay, in the question of calculating the distance traveled by our car, what we're trying to persuade ourselves of basically is that what we should be trying to get at is the area under our speed graph. So let's see why that should be true. So as the number of subintervals in our estimates increase, so again, remember, we're sort of assuming that the speed is constant over each subinterval so that we can calculate the distance traveled in each subinterval. So as the number of subintervals increases and their width decreases, the red rectangles in the picture had 30 of them, but if we take 60 or 120 or whatever, the red rectangles in the picture come closer and closer to filling all the area under the speed graph. And the true distance traveled is the limit of these improving estimates as the length of the subintervals approaches 0 and the number of them goes to infinity. And that's exactly the area under the speed graph. So those little white triangles that were being left out, they're shrinking as the estimates increase, as the number of subintervals increases and their width decreases. Okay, so the true distance traveled is the limit of that process, which is exactly the area under the speed graph between 0 and 60. So for this particular problem, we can now assert more confidently that the answer should be 900 meters, which is the area under the graph. Just to point out the fact that we can calculate this for this particular example is just sort of a feature of the simple example that we're looking at, where the area under the graph happens to just consist of a triangle and a rectangle whose dimensions we know. So the fact that we can actually calculate the area here is because it's an easy example where the region is just a rectangle with a triangle sitting on top of it. Okay, generally, the argument that says that the distance traveled by the car should be the area enclosed over the relevant interval under the graph of its speed against time, that argument should apply in general, whether or not that area is something that we can calculate. Okay, so the sort of two things to take away from this lecture, or one thing to take away from it anyway, I guess, is this idea that the total distance traveled should be the area under the graph of speed against time. That's one of the things. And the other thing to take away from it is this idea of estimating that by taking sort of partitions of the interval into these small parts, where you assume that the speed might stay constant over each subinterval, and refining that estimate by taking more and narrower subintervals, and eventually looking at a limit of that process as the width of the subinterval goes to 0. Okay, so a remark, this is something that you might have a chance to think about today. With some careful attention, you could check that if we were to split the 1 minute into n subintervals, so each of them would have width or duration 60 over n seconds, and estimate the distance traveled as we did, then the answer would be 900 minus 300 over n. So basically the picture there would be, you'd have these vertical columns that you'd have, each one of them would have width 60 over n, that would be sort of the base for the rectangles in your picture, and the height of each one would be the speed that the car is traveling at the start of that subinterval. So if you're on, if you're on the fourth subinterval, you've completed 4 over n parts of your acceleration, so you can figure out the height that the fourth rectangle should have, and you should be, and you can, if you just go through the details there, you'll be able to find that the estimate for the distance traveled, where you take n subintervals, all of the same length, 60 over n, would be 900 minus 300 over n, and we can observe that the limit of that expression as n goes to infinity is 900. Okay, so the idea here applies much more generally. For example, if you had some function defined by a formula, and let's say that you knew what the formula was, so the graph of your function would be y equals fx, you're interested in some interval, and your graph looks like this. And let's say that you know what, let's say you have a formula that tells you what f of x is. Then if for some reason, and again, we'll see some more examples of reasons why you might want to do this. If for some reason you wanted to calculate the area under the graph of your function, a way of approaching that problem would be to split the interval up into subintervals exactly as we did. For each of the subintervals, if the function is something with a formula that defines it, we can calculate the value of the function at the left-hand endpoint of our subinterval. Just pretend that the value of the function stayed constant over that subinterval, and estimate the area of that subinterval just as the area of the rectangle, which it would be if it did stay constant. Same thing for the second one. We get a picture like this, and so on. So the thesis here is that we're actually able to plug in the left-hand endpoints into a formula for f. We know what they are, so we know what the heights of these various rectangles are. We can calculate their areas, add them up. That's an approximation to the area that's shaded in blue there under the curve. And the premise is, or the thesis is, that you can get a true picture of the area by taking a limit of that process as the number of subintervals increases to infinity and the width of each individual one decreases to 0. Of course, whether you can actually calculate that for a given f or not probably depends on what the f is and what computational and technical resources might be, and theoretical resources might be available to you. But that's the idea. It's kind of it's an idea of estimating areas by taking these approximations via columns and then taking a limit of that process as the number of columns goes to 0, goes to infinity, and the width of each individual one goes to 0. So it's something like taking a sum, but it's kind of a limit in the process of taking a sum towards the case where the sort of number of things you're adding together kind of is becoming infinite, and the sort of width of each one of them is going to 0. And this is what they call a definite interval. So I guess the point of this first lecture today is that concept of estimating an area by taking this collection of vertical columns, which are rectangles, adding their areas together and taking the limit of that process as the number of columns goes to infinity and their width goes to 0. That's a key concept of integration. And the fact that it actually describes things that arise in physical reality, such as the distance traveled by a moving object, if you know how its speed is varying over time. So those are the two things to take away really from this first lecture. Thank you very much, everyone. Our second lecture will be recorded at 10 o'clock on Thursday, and everyone hopefully has the links for that at this stage. So see you on Thursday, everybody. Thank you very much.